Welcome back to my YouTube channel. Today we're talking about an introduction into the biochemistry of sugars. This is not going to be a super comprehensive, meaning it's not going to cover every single thing you can possibly think of concerning sugars. Instead, what we're going to cover is really two primary things, and it's not going to make sense if I say them right now, but they will later. Those two primary things are the conversion between linear and cyclic forms of monosaccharides, and the conversion between mono and disaccharides through glycosidic bonds. Again, that doesn't mean anything to you right now, but it will hopefully soon later. The way I want to structure this video is these seven, I want to structure it into 7 parts, as you can see in this little note card I've drawn right here. And those parts is, first, I want to talk about a few definitions of a lot of the words and structures and processes that we're going to go over. Second, I want to talk about some of the common sugars, their common names, and the structures pertaining to each one of them. Third, I want to talk about a process called mutarotation. Fourth, I want to talk about glycoside formation, or the bond formation. Fifth, I want to talk about a few quick reactions pertaining to oxidation reduction and two tests, and 2 reactions involving adding or removing from a carbon backbone of a sugar. 6, I want to talk about disaccharides, and then lastly, 7, I want to talk about polysaccharides. So let's first look at the definitions. First, before I get to the definitions, I want to emphasize the reason why I'm going over these definitions in this way, or I'm just doing it first, is because while it will seem confusing to you right now, it hopefully will allow you to go into the next parts of this video with some background knowledge, even though it might be a little bit confusing background knowledge of what we're about to talk about next, so you can kind of put the puzzle pieces together, hopefully. That's my hope for talking about these definitions. So they will be confusing now, but hopefully they'll be make a little more sense when we start putting everything together in moments. So let's talk about the first one. So what is a carbohydrate? So obviously this entire video is about carbohydrates, which is also synonymous with sugars. And everyone knows that a sugar is, it's something to eat, it's something that gives you energy, it's something that gives you life. A carbohydrate is one of the 4 macromolecules that you find within biology and biochemistry, those sorts of things. The 4 macromolecules, and we're not going to talk about the other ones, I'm just going to list them just for context, I suppose, are carbohydrates, which is what we're talking about, lipids, proteins, and nucleic acids. Carbohydrates is one way that you can what you can call it, I suppose, is a polyhydroxyl aldehyde or ketone. So polyhydroxyl aldehyde or polyhydroxyl ketone. And that might not make sense right now, we'll get into it later, but one of the ways we can think about how this name makes sense in terms of what it has, what it's made of, is think about the name. So polyhydroxyl, poly means many, hydroxyl means, as we're going to talk about later, OH. And the aldehyde or ketone indicates whether or not it's an aldose or a ketose sugar. That's probably as confusing now, it'll make more sense later. So second, so definitions 2 through 5 all have to do with the naming of a sugar based off of how many sugars are contained within this unit molecule. So in other words, four of these words have a prefix of mono, di, oligo, or poly, and a root word of saccharides, and saccharides meaning sugar, and the first prefix pertains to the number of the saccharides. So it's pretty intuitive. You can look at the name of the word, and be able to determine what it means. So monosaccharides obviously means 1. So this is one singular unit of sugar. Disaccharides mean 2, so there's 2. Oligosaccharides means there's anywhere between 2 and 10. And then polysaccharides is anything 10 and above. And usually with polysaccharides, one of the interesting things about it is that as you see with these previous ones, mono, di, and oligo, they kind of progress at a pretty slow rate. But with polysaccharides, you actually progress much faster, and polysaccharides get much bigger than just 10. So yeah, and then these 3 definitions here, aldehyde, ketone, and OH, which is hydroxy or alcohol, which has to do with this context for the OH, what that means. These are 3 really basic functional groups in organic chemistry. I just want to reference them just in case you don't know what they are, therefore you don't get lost later on. An aldehyde is this first one right here, which is simply a carbon, which is this little inflection point in this triangle right here. That's what that represents, even though it's not written there. That's a carbon double bonded, those 2 lines, to an oxygen, and it's also bonded to other things. It's bonded to a hydrogen, this H, and it's bonded to this R group, which is usually an alkyl group or a carbon. That's an aldehyde. A ketone is the exact same thing as an aldehyde, except instead of having a hydrogen bonded to this carbonyl carbon, it has 2 alkyl groups, or 2 R groups, or 2 carbons bonded to that central carbonyl carbon. And then next we have isomers. So all these other definitions kind of have to do with each other. and it had to do with this idea of isomerization. So what an isomer is basically when you have two molecules with the exact same number and exact same type of atoms. So it has the exact same, on paper, it has the exact same chemical formula, but they're different in the way, there's some other differences about them other than just the fact that they have the same number and same type of atoms. And that can be either one of two things, really. Either they're a constitutional isomer or a stereochemical isomer. A constitutional isomer has to do with the fact of it having a different connectivity, meaning this atom is bonded to this atom and it's bonded to this atom and it's bonded to this atom. So two constitutional isomers, they might have the exact same chemical formula, but what differs between them is the fact that they're bonded, they're arranged and organized differently in the sense that this thing's connected to this thing, this thing's connected to this thing, and their difference is that they might have different connectivity, hence the name. And then a stereochemical isomer is two molecules with the exact same formula, exact same number of atoms, exact type of atoms, and they're actually connected the same ways, as in this thing is connected to this thing and that and such. But what difference between two isomers, two stereochemical isomers, is the fact that they're oriented in space differently. And this might not seem like a big deal at first. You might think, oh, that means nothing. Why would I care about orientation in space? But what you will find out later is that this orientation in space has a lot to do with its chemical makeup, its chemical behavior, and a lot of other stuff. So, and then what is this? 11th, we have a chiral center. So chiral center has to do with a stereochemical isomer. The chiral center is essentially a tetrahedral molecule, meaning it's and usually carbon in this case, that is bonded to four other things. So it has four other constituents of four other atoms bonded to it that are non-identical. So if it has like two hydrogens and it has two something else, it can't be a chiral center because it has those two hydrogens. Therefore, it can be superimposed on itself. This chiral center, this particular part of a larger molecule. And the idea of a chiral center is that it changes as long as if it's not a molecule that's symmetrical as a whole, it changes its stereochemical behavior. And it has more to do with this later. So, and then 12th and 13th both also have to do with each other as well. And an enantiomer is basically two stereochemical isomers, which are opposites of each other. So they're the exact opposite of each other. They're still non-superimposable on each other, meaning no matter how you rotate or turn and whatnot, you can't exactly get them to match up, kind of like your right and left hands. But they are opposite each other. Like your right hand and your left hand are opposite each other, but you can't rotate them a certain way to make it completely match. And an example of this molecule is D-glucose and L-glucose. The D and the L stand for dextrorotatory, and the L stands for levorotatory. I will talk about this more later, but if you just look at them, these are enantiomers of each other, meaning that they're actually just exact opposite each other. So if you notice all these lines going out, which indicate hydroxyl groups, they're just the exact opposite each other. That's all it is. And then secondly, we have a diastereomer. An diastereomer is basically two stereochemical isomers that are not, they're just not enantiomers, anything but enantiomers. So they differ at more than one place. Okay, so 14th, we have an anomeric carbon. The anomeric carbon is the carbon atom in a cyclic carbohydrate that was previously the carbonyl carbon in the sugar's linear form, which will become a new stereocenter or a chiral center upon cyclization. And so the idea is that in a process that we'll go over in a few moments called mutarotation, the linear form of glucose converts into the cyclic form naturally on its own. And in doing so, when we number the carbons in the sugar molecule, we number it 1 through 6. Number 1 beginning with the aldehyde or the ketone, or in other words, the carbonyl carbon, and you go all the way down. And the idea is that an anomeric carbon is the carbon that was the carbonyl, or in other words, carbon number 1 in the linear form. And then when it becomes the cyclic form, it will wrap around. And the anomeric carbon is just simply the number 1 carbon. And it's important because the anomeric carbon is what will form the glycosidic bonds with an aglyconic component to make a glycoside. We'll talk about that in a few moments. 15th with an epimer. Epimer is just two diastereomers that differ in only one place, or only one chiral center. Otherwise, they're the exact same. 16th, we actually have 4 things: acetyl, ketol, hemiacetal, and hemiketal. I have them written right here. These 4 things right here, they're all tetrahedral structures with 4 different substituents. So first, let me tell you the names of each of these. I want to tell you how I kind of think about how to determine what it is based off the name. So first, this is an acetal, this is a ketol, this is a hemiacetal, and this is a hemiketol. So the way I think about determining the structure of it based off of the name is that acetal is more closely resembling to aldehyde, and ketol is more resembling, the name is more resembling to ketone. And like we know before, an aldehyde has a hydrogen attached to it, and a ketone doesn't, it has another carbon. And it's the same thing with the acetal and the ketol, in the sense that the acetal has a hydrogen, this right here, and an R group, whereas the ketol has no hydrogen there, it just has 2 R groups. Other than that, acetals and ketols are the exact same in the sense that they both have 2 alkoxy groups, which is these ORs, as these 2 alkoxy groups. And then as for the hemi versions of each of these, so hemiacetal and hemiketol, the only thing that differs between the hemi version is the fact that one of the alkoxy groups is replaced with a hydroxy group. And then 17 and 18, we have furanose and pyranose. So furanose and pyranose are the 2 possible forms of the cyclic form of a sugar whenever it converts via mutation from linear to cyclic. And the idea is that a furanose is simply a 5-membered ring, 4 carbons, 1 oxygen, and a pyranose is that but plus 1 more carbon. So in other words, a 6-membered ring with 5 carbons and 1 oxygen. And the way we get its name, or the way we get the name of it, is based off of a similar molecule, or 2 similar molecules for each one of them, or 1 similar molecule for each one of them, therefore there's 2 total, which is furan, which is this, and purine, which is this. They're basically the exact same thing in the sense that furanose and furan both have the same number of carbons, the same number of oxygens, and purine also is the same number each. It's just that furanose has hydroxyl groups attached throughout it, and furan doesn't. It just has a double bond and then hydrogens in order to be saturated and neutral. So that's just kind of how we get the naming of it. This next page right here, I want to introduce you to some of the common saccharides. I want to tell you about kind of the way that you look at that and read that, and also a way for each of them to kind of remember where their hydroxyl groups are oriented in space, based off of these kind of like little easy mental shortcuts, I guess. First, I want to note is that the way we read each one of these, in case you didn't know, is that each one of these little inflection points, where you have this point right here where it has the line connected to this hydrogen, this line connected to this OH, this little inflection point for each one of these represents a carbon, even though it's not explicitly drawn. And then for all of these, they're all similar in the fact that they will have a carbonyl carbon somewhere, usually at the top, near the top. If it's an aldehyde, it's an aldose, and if it's a ketone, it's a ketose. And then the aldoses all have their aldehyde part at the very top of it, or the head, which you can see here, here, and here. And then fructose is the only exception in the sense that it has a ketone, therefore it's a ketose, and it can't have its carbonyl carbon at the very top because, again, since it's a ketone, it has to have 2 carbons bonded to that carbonyl carbon, which, again, the carbonyl carbon is this one right here. And therefore, it can't be at the very top because it has to have some other carbon attached to it, so that's why it's placed where it's placed. Next, I want to talk about what does the D mean. So the D stands for dextrorotatory. Dextrorotatory basically means that this fifth hydroxy group, and again, the reason why it's this is carbon number 1, 2, 3, 4, 5, and I guess 6, but this fifth one right here, this hydroxyl, D basically means that it's oriented to the right, and it stands for dextrorotatory. L means that it's oriented to the left, and then everything else would be kind of mirror opposites of each other. So everything would be opposite here. Just like if you look at this little picture right here, you have D glucose and L glucose. D means that it's on the right. This last one, these little dashes each represents hydroxyls, and of course you have to just imply that the hydrogen is on the other side of the hydroxyl. And this D, you have this very last hydroxyl group right here, or not the very last. This is the last one. This is the fifth one. It's to the right. L means it's to the left. Therefore, everything else also corresponds with it being to the left. So these are two enantiomers. They're opposites of each other. So yeah, and so the way that I remember these 5 common things is, first, here we got ribose. If you notice ribose, it has all of the hydroxy groups. If it's D, it's all on the right, and again, if it's L, it's on the left. But the idea of ribose is, when I think of D-ribose, I think they're all right. as in with the R and ribose. So they're all hydroxyls are all on the exact same side. And then for glucose, this is the most common saccharide. It's the most crucial to understanding all these other biochemistry things. Glucose, you can kind of just imagine it's gonna sound weird, but D-glucose or L-glucose, either one, you imagine it like there's like a middle finger here. So you know how these like fingers, this is finger number 1, 2, 3, and 4, and then you can just like mentally draw a picture of whoop, whoop, here's the middle finger, and then here's your other fingers, right? That's just a possible mental shortcut if you want to. D-mannose, I think of man and the mannose part, and I think this is like the shape of a trigger of a gun, so that here's like the bloop. And again, this sounds silly, this might not help you, this helped me. That's how I imagine it. D-mannose, man, manly, gun, trigger, gun, that sort of thing. And then next we have galactose. Galactose is essentially the exact same of glucose, except for it's an epimer at C4. So in other words, it only differs at carbon number 4. Otherwise, the exact same thing of glucose. And then fructose, lastly, is just the ketose version of glucose. So it's basically the exact same thing, except it's a ketone, or making it a ketose. Therefore, you have to put the carbonyl carbon where it is. Okay. So let's talk about a process called mutarotation. The idea of mutarotation is that whenever you have glucose in solution, it's actually not going to stay in this. It's not going to stay in this straight chain form that we've got written out right here. Instead, what it's going to, or most of it's not going to. Maybe like a very, 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 very small percentage is. But because it's thermodynamically favorable and just energetically favorable, and it's a better lower state of potential energy, that sort of thing, what it actually does is it undergoes an internal cyclization called mutarotation. And the idea of it is it kind of just wraps around in on itself. And as you can see here, the oxygen of this hydroxy group here, I don't know why I keep saying this one's last, of the fifth hydroxy group is actually going to react with the carbon and the oxygen of the carbonyl group, and it's going to form either pyranose or furanose, depending really on whether or not it's an aldose or ketose. I mean, technically, even though you have an aldose in solution, it can also interconvert into a furanose, but it's very, very, very small amount. And when it converts into the cyclic form, you actually have two versions that it can possibly go into, called the alpha and the beta. And this idea of alpha and beta is going to be really big for these next sections. So the idea of the alpha versus the beta has to do with this part right here. Again, this is the anomeric carbon. If you number it, this is 1, 2, 3, 4, 5, 6. And then we can number it again right here, 1, 2, 3, 4, 5, 6. And then again, this right here is the anomeric carbon. Like I said before, it's carbon number 1, it was the carbonyl carbon. And whether or not this hydroxyl group of the anomeric carbon that it forms by breaking the pi bond between its oxygen atom and forming a new one with this other oxygen atom, whether or not this hydroxyl group is oriented away from or towards this last tail hydroxy group, so this very last one, if it's oriented away from, it's alpha. If it's oriented towards, it's beta. And this also plays another idea with glycosidic bonds. So in other words, we're going to talk about this in a second, or I guess we could just go ahead and talk about it. One more thing though, before we do that, which is that in solution, naturally it will reach equilibrium, meaning it will naturally become mostly the beta form, a little bit of the alpha form, and almost a very tiny bit of the linear straight form as it interconverts between the different ones. So what is a glycoside? So a glycoside is the next part of this video. The basic idea is that you go from a monosaccharide to a disaccharide via a formation of a glycoside bond. And basically the idea of a glycoside bond is that this anomeric carbon, you will add something to it such that it will no longer, the thing you add to it is called an aglyconic, the aglycon part, and the part that was originally the carbohydrate is the glyconic part. And the idea is when you add something to it, it goes from the hemiacetal part, which is again, this is the anomeric carbon, to an acetal, and this other oxygen and this, whatever is attached to this R, basically prevents it from continuing to go through mutarotation. And I know that sounds weird, but just look back over here, okay? So this is the anomeric carbon. Like I said, we numbered it 1, 2, 3, 4, 5, 6, and then we numbered it here. This is the anomeric carbon. What we're gonna do is we're basically gonna react it with acid. We're going to react it with some sort of aglyconic part in the presence of acid. The acid is going to deprotonate the anomeric carbon's hydroxy group. It's going to protonate it. And what's going to happen is that now that you protonate it, this is going to be H2O, this little substitute here. And since it's water, therefore it's a good leaving group, so it's going to leave. And that's what happens here. So this acid, HCl, hydrochloric acid, donates a hydrogen to the hydroxy group of the anomeric carbon. And then it's water, so it's a good leaving group, and then it leaves, and then you have a cation, it's positively charged, and that's when the aglyconic component comes into play. In this case, we have methanol. Methanol being that it's the all part indicates alcohol, and the meth indicates it has one singular alcohol component to it, so that's why it's called methanol. And the idea is that in this case, we have an aglycone plus the sugar, and this is going to go forwards and backwards. When we form the glycoside, this glycoside can be in the form of a disaccharide, being that this methanol can be replaced with another sugar, and it also produces water, as does any other condensation reaction. The hydrolysis, you're going to do the reverse so that you can get the reagents as opposed to the products. And the idea is that with this positively charged cation right here, the methanol, or in other words, the aglyconic part that's going to add to the anomeric cation, can attack from either the above or below. And whether or not it attacks from above below determines whether or not you form a beta or an alpha. Because again, like I said, whenever you add something, whatever is the substituent of the anomeric carbon that isn't hydrogen, whether or not it's oriented up or down, determines whether or not it's alpha or beta. And if it's oriented down away from this hydroxy group, it's going to be alpha. And if it's oriented towards, it's going to be beta. And that's what you kind of see right here. And again, so what's going to happen is hydrochloric acid donates a proton, OH becomes H2O, therefore it's a good leaving group, so it leaves behind a cation, and then methanol is going to add itself because this nucleophilic oxygen right here, part of the alcohol group, is going to add itself, and then it's going to be positively charged because it has 3 connections, oxygen does in this part, in this intermediate, and then the intermediate's actually going to lose a hydrogen thanks to the chloride ion. And then essentially what you end up with is just this neutrally charged OCH3 that's been added to the anomeric carbon. And again, because of the presence of this, it prevents butyrotation. And in this case, if you wanted a disaccharide, in other words, you wanted 2 if you wanted 2 sugars added to each other, this methanol will be replaced with a sugar. And as you can see here, the reason why, again, alpha means it's oriented away. This is the hydroxy group we're comparing it to. As you can see, it is on the axial part of the structure, so it's pointing down. And then here we have an equatorial, meaning it's pointing closer towards it. So that's how you kind of like look at that and determine. And then here's a few quick reactions. So the reactions that we're going to talk about here is we're going to talk about 2 tests, Benedict's and Toland's. And then we're talking about a couple different ways to oxidize and then a way to reduce. And then lastly, on another piece of paper, we're going to talk about how you can lengthen the carbon backbone by 1 carbon, or you can shorten it by 1 carbon. So let's talk about this first one. Benedict's test is basically a test to determine whether or not a given sugar is a reducing sugar. But what is a reducing sugar? A reducing sugar is any sugar that can be oxidized by metal ions. In the case of Benedict's test, this case is copper. To oxidize it to become a carboxylic acid or a carboxylate ion at that aldehyde portion of it, of the aldose. And the idea is that this is a redox reaction, so the aldehyde component of the aldose of the sugar is becoming oxidized, and then the copper ions are becoming reduced. And the way that you actually do this test in real life is that you just react a given unknown sugar. Again, you want to determine whether or not it's the reducing sugar with the reagents of the Benedict's test, and then you heat it. And then if it is a reducing sugar, it will actually cause the redox reaction to happen. And then one of the products of the redox reaction is this and this reduced copper. And the reduced copper will actually cause a color change, and it's based off the color change, so you can determine whether or not it was a reducing sugar in the first place. Then Toland's test is the second test. Is the same idea, except instead of copper, use silver. And the difference between it is that there's no color change in a sense. What actually happens is that silver will actually start to, like metallic silver, will start to form on the walls of the reaction vessel. And then here we have two different ways you can oxidize. There's actually a third one with periodic acid, but it's such a strong oxidizing agent with periodic acid that it will actually fracture the carbon backbone. So I just didn't include it. But here we can oxidize the aldehyde component of an aldose using either bromine or nitric acid, both of which are oxidizing agents. And what essentially just happens is we react the aldose with bromine and water. It just simply is an oxidizing agent. So all it's going to do is just add oxygen to the hydrogen component of the aldehyde, therefore rendering it a carboxylic acid at that part. Nitric acid is a stronger oxidizing agent, which will actually cause this other carbon at the very bottom to also be oxidized. So the difference between the two is just that bromine is weaker and nitric acid is stronger, and then periodic acid is actually so strong that it will fracture the carbon backbone. And then here we have reduction. You can actually reduce aldoses or ketosis using sodium borohydride. It's kind of hard to read because I've written it so small, in the presence of also with water. And then of course, intuitively, because of their structure, an aldose will yield a primary alcohol and a ketone will yield a secondary alcohol. And this has to do just with the fact that, ketone has two carbons attached to the carbenyl carbon, therefore of course it would produce the secondary as opposed to the primary with the aldose. And then all that's happening is you're just losing this oxygen. That's the idea of reduction. Reduction is gaining the electrons, and oxidation is losing. So that's why you lost the oxygen. And so actually, before we go there, I wanted to mention, I forgot to mention this. This is the D-aldose family. Basically, the idea of this, I forgot to mention this. The idea of this is that these are the different possible configurations you can have of aldoses. And all of these have common names. And basically, these are all just the different ways you can put it together given a certain amount of carbons. And these are all the common names to them. So now let's talk about disaccharides. So the idea, again, with the disaccharides, you go from a monosaccharide to disaccharide by basically reacting with the formation of a glycosidic bond. And so the idea is that one of the main ideas of this is that you're going to have either alpha or beta glycosidic linkages between the two glucose molecules. Again, in this case, the aglyconic part would actually not be just simply methanol, but rather another sugar molecule. And alpha just simply means that it is oriented away from the last hydroxy group of the first one, and beta means that it's oriented towards the last one. So here are 4 really common disaccharides, and basically the difference between all these different ones has to do with what they're made of, as well as the type of glycosidic bond. Lactose is simply glucose and galactose bonded together, either in alpha or beta forms. Maltose is 2 glucoses, specifically through alpha linkages. Again, that means that we can digest it. If it's beta, such as with cellulose, can't digest it because we don't have the right enzymes. Sucrose is just simply glucose plus fructose. And then lastly, we have polysaccharides. So with polysaccharides, there's really 3 main big players that I want to talk about real quick. That has to do with starch, glycogen, and cellulose. And these are all kind of related to each other. But starch, what a starch is just many alpha glucoses linked together through either alpha 1,4 glycosidic bonds or alpha 1,6 bonds. And you can actually have 2 components in it. Again, like I said, it's very long, very big. The amylose, and so what we define starch is that there's 2 components to it. It's either the amylose, the linear part, or the amylopectin, which is the branches that you will have from the amylose part. And the idea, again, is you will have 1,4 bonds with amylose. So you can, again, this is the anomeric carbon, this is 1, and then And this other one, this is 1, so you go 1, 2, 3, 4. So this is 1 and 4. That's why you call it 1 and 4. And again, it's glycosidic because of what we said before. And then for the branched parts of amylopectin, you have 1, 6, meaning, like I said before, this is number 1, and then this is number 1 on this one. So you go 1, 2, 3, 4, 5, 6. And so that's kind of like where that comes from. And then lastly, we have glycogen and cellulose. Glycogen, then these are really similar in the sense that they're kind of just like starch, except a little different. Glycogen is just animal starch, in the sense that it is mostly amylopectin, meaning it has a lot, it's much, much more branched, and it's also usually much heavier and bigger than normal starch. And then lastly, cellulose is basically just amylose, again, this being amylose, but with beta 1,4 linkages, which means that we can't digest it because we can't digest beta linkages. So I think that's it. I'm trying to think of anything else, but I think that's it. So I actually completely forgot to go over these last 2 reactions. I don't know how I forgot to do this, and I didn't want to redo the entire video, so I just figured I would do this here and then edit it in at the very end. So the first one is these 2, the Killian-Fischer synthesis and the rough degradation. The idea of both of these is that you're actually going to either add to the carbon backbone of an aldose exactly 1 carbon, or you're going to remove 1, and that's what they do. So here we go. Here for Killian-Fischer, all you're going to do is you're going to react the aldose with the hydrogen cyanide, and then the cyanide portion of the hydrogen cyanide is going to add to the carbonyl carbon, and then the hydrogen part of the hydrogen cyanide is going to add to the oxygen part of the aldehyde, and after that you're going to react it with barium hydroxide and in the presence also with acid, and then all that's going to do is it's going to remove the nitrogen part of the cyanide and replace it with OH. So that and this new, and the carbon of the hydrogen cyanide is what's going to form the new carbon to add to the carbon backbone. And then rough degradation, the idea of this is you're going to shorten it by 1 carbon, and all you're going to do is you're going to oxidize it first using bromine and water like we talked about before, so that you convert the aldehyde part of the aldose to a carboxylic acid, and after that you react with hydrogen peroxide as well as with iron. And what that's going to do is it's going to oxidize even further, and it's going to remove this carbon as CO2, shortening it by 1 and rendering it the aldose like it was before, just without one of the carbons.